So now I'm trying to keep track of the number of fours if I roll 8 dice, and I want to check again, is it binomial? So on each single die, I have 2 outcomes. I get a 4 or not. And I have a fixed number of trials. That would be the 8 dice that I'm rolling. I'm going to keep track on each one. And each die is independent of the others. And then my fourth condition is the probability of success, which in this case is I get a 4, is fixed at 1/6. So it is binomial. Here are some non-examples. 10 cards dealt from a standard deck. I'm keeping track of the number of red cards. So I do in fact have 2 outcomes, of course, red or black. I do in fact have a fixed number of trials, which is 10 because I'm dealing 10 cards. Each card, however, is not independent because as I deal them, the probability is changing. So, for example, after I deal the first card, dependent upon whether or not it was red or black determines the probability for my next card. So the cards are not independent. Ooh, helpful if I could actually spell, right? Independent. The next one, number of foul shots made in a basketball game. So of course I do have 2 outcomes. I make or I miss it. But I don't know how many trials because it doesn't say how many foul shots I'm making. So right away, this one is also not binomial. You like these fancy Christmas colors? Me too! Some notation that you'll recall perhaps from Algebra 2 and Pre-Calc. If I want to, in order to go back and do the probability distribution tables, I'm going to be using my combination notation. Another fancy way to write it is this. Means the same thing. Your calculator, of course, uses this one. And if you remember what it means, it's n factorial over r factorial times n minus r factorial. And of course, n is the number of trials, and r is the number of successes I'm looking for. Remember, we use that word success loosely. So, for example, here I've written S for success and F for failures. And so if I'm trying to figure out the probability that the number of successes, something like this, that S equals 3, I'm going to look at the combination notation, and then I want to have, so I'm actually going to come over here and call this R. And so I'll want to have R successes, because I said that's what I wanted, which means then that the failures have to be N minus R. That'll make a little more sense when we actually start doing these. And then one key concept is, as the number of samples that we use gets really large, so as N gets really large, the binomial distribution gets approximately normal. And because that happens, I can switch over to using, so I can go from a binomial problem to a normal problem. And I'm going to show you the formulas here in a second. These formulas are on your formula sheet for binomial distributions. If I want to find the mean for a binomial, then the mean is equal to n times p. Remember, we defined those up above, where n is the number of trials and p is probability of success. And the standard deviation is equal to the square root of that mean times 1 minus p. Now, I can switch to normal approximation, but I have to check a couple of conditions. And that is that n times p has to be greater than or equal to 10, and then n times 1 minus p also has to be greater than or equal to 10. And so if that's true, then it becomes normal, and mu, remember, is, we just defined it as n times p, and standard deviation would turn into the value for n times p times 1 minus p. And then I could just treat it as though it's a normal approximation. So keep in mind that we're going to do some problems in class, and I'm going to show you how to do them both by hand and by calculator. On the AP test, they would simply show you the by hand setup, but if you had to actually come up with the value, you'll want to use your calculator to do it. So if you go to second vars, where your distribution stuff is, and that's where normal distribution was and inverse normal. If you go down far enough, or you could even go up, sometimes I shortcut and go up, you'll find both binomial PDF and binomial CDF. PDF we use when we're finding an individual probability. So it would look something like this. The probability that x is equal to 3, just 1. But CDF is cumulative, so we'll use that when we're finding a sum, or we could say more than 1, more than an individual. And so it's going to look like something like this. It could say probability that x is less than or equal to 2. It could say probability that x is greater than or equal to 5. And the way that it works is that in the calculator, it adds up from the beginning to whatever number you're searching for. And so what we're going to find is, because these are discrete distributions, you're going to have your bars. We've drawn a few of these in chapter 7 showing the individual probabilities. So this might look like this, and keeping track of the individual probabilities. And so binomial PDF will find an individual bar. so 1 bar in the histogram. But CDF, it adds them up. So if I'm doing less than or equal to 2, it'll sum up this for these first 3 bars. Now, here's where it gets tricky, is if I want greater than or equal to, so let's say I want to do greater than or equal to, or let's just do greater than 1. So now I would want the 2 bar and the 3 bar and the 4 bar, but CDF is only going to do 1 from 0 to the end of wherever I say. So if I want stuff that's later in the picture, I'll have to figure out which ones I don't want. So in this case, I don't want 0 and 1. And then I have to remember that the entire picture equals 1, so I would want to do 1 minus the probability that x is less than or equal to 1. And so I'll take 1 and then I'll subtract these first 2 bars, and then that will give me the yellow. You'll get lots of practice at this.